So this is just a brief concept bite on the concepts of activity and the debye-huckel theory. So activity is technically the term we should be using whenever we think about things like equilibrium constants. We always say an equilibrium constant has no unit, and it's because it's based off activity. And all activity is it's a measure of the effective concentration. So what we find out is, particularly when concentrations are very high, the concentration that we actually see reacting is different to the concentration we think is in solution. But it is actually the same as the activity of the solution. And this comes from the fact that no solution is ideal. The higher the concentration, the further away from ideality I am. In a solution that is ideal, all interactions should be the same, but this very rarely happens. And particularly when I have ionic solutions where I have positive and negative charges, my interactions between those positive and negative charges are very different than between pure solvent molecules on their own. So when I have interactions between the anions and the cations of the solute, or whether I have interactions between the ions in the solute and the solution, they're very different, and this leads to a non-ideal solution. What we find is that whilst all solutions will deviate from ideality, it's particularly significant for ionic solutions. Now, some of the consequences of that are things like if we were to record pH is an ionic process, and what we would find is that if we were to record the process of a nominally high concentration acid, so say 1 molar HCl, what we would find is the pH of that wouldn't be 0 as would be predicted. It would actually be a number bigger than 0, and that's because of this effect of non-ideality within my solution. This also affects other factors such as solubility, which we've already met in this course, and things like driving forces if I was to have a redox reaction or something like that with a chemical potential associated with it. Now, activity is given to me by quite a simple equation which relates the molality to the activity by this constant, the activity coefficient, given the symbol gamma. Now, when the concentration is low, the molality and the molarity are essentially the same and can be interchanged, but this deviation becomes higher as the concentration of the solution increases. The activity constant, as I've already said, the activity coefficient will be less than 1. My deviation is always going to be less than 1. And so my activity is always lower than the molality in the solution. This term B Plimsoll symbol, or B standard state, is just to account for units. Neither the activity nor the activity coefficient have units, however molality does. And so all it's there for is to account for the units on either molality or molarity. It has the value of 1 and the appropriate units, and that just helps it cancel things out. Now, the debye-huckel is a way for me to calculate this activity coefficient, gamma, from the previous slide. It calculates a value of something called the ionic strength, which is essentially just a measure of how the ions are in solution, the effective concentration of ions, and takes into account differences in charge and things like this on the ions. And in an ionic solution, the debye-huckel will give an activity coefficient which is the same for all of the ions in the solution. Now, debye-huckel makes a few assumptions, the first of which is that if we have ions in solution, there will be Coulombic interactions between them, and that will lead to non-ideality. The rest are kind of all a little bit more particular. So things like ions are spherical, they're not polarized by any electric field, and that the solvation of an ion only affects its effective ion size, plays no other role. It also assumes that ions are fully dissociated, so this affects things like weak acids, where debye-huckel is a very poor method for calculating the activity of a weak acid or a weak base. More complicated assumptions are things like there being no electrostriction, so there is no change in shape of my ions when they dissolve. I'm always going to assume things as spherical. And it has a kind of an obvious consequence that we say that there's an ionic atmosphere around each ion, and that just means that positive charges are more likely to have negative charges nearby, just from this charge-charge interaction. The most limiting thing about the debye-huckel assumption, though, is that it only works at low concentrations, and low concentrations is something that we define poorly. But you'll see that if you do some calculations, even at moderate concentrations, the deviation of the ionic strength and therefore the deviation of the activity from the concentration can be quite marked. So what the debye-huckel theory does is it calculates this value of the ionic strength, which is capital I. And the ionic strength is related to the charge on the ions, the concentration of the solution, and ultimately all we do is sum that up for all of the different ions in solution. So if I have 2 types of ions in solutions, or 3 or 10 or 50, all I do to work out my ionic strength is just to add them all up in turn. And I can calculate the activity coefficient because it relates to this value for the ionic strength for the charges in solution, and it also relates to a constant A, which is dependent upon the solvent that we're using and the temperature of that solvent. It's actually related to the dielectric constant, or how well the electric field is seen through the solvent. Once I know gamma, I can easily work out the activity coefficient. If I do this for most ionic solutions, I'll find out that even at moderately low concentrations, the deviation can be quite significant. And in the case of 1 molar acid, I actually tend to only see about 40%, perhaps even less, of the effective charge as I would do with the real charge. So a 1 molar acid actually only behaves like a 0.4 molar acid. I hope this has been useful. I'll be back with more.